All right, so now we're going to look at fixed point iterations. And if you will, the motivation for studying fixed point iterations is that we're going to be able to cast sort of root finding methods like Newton's method as a fixed point iteration. And so by establishing general convergence results about fixed point iterations, we can then apply that to understanding Newton's method, for example. So let me define for you what a fixed point is first and foremost, right? So a fixed point of a function g of x is any point alpha for which g of alpha is equal to alpha. Okay, so let me sort of just draw something for you. So if this is g of x, right, and this is the y equals to x line, and that point, the intersection point, is a fixed point of the function g of x. Okay. All right, so let's look at examples of this. Right, so if you have g of x is sine of x, for example, then it's easy to check that g of 0 is 0, so alpha equals to 0 is a fixed point of sine of x. Okay, so I should remark that not every function has a fixed point. So examples of functions which don't have fixed points are e to the x, the natural log of x, say x squared plus 2, and so on. So there are a bunch of functions for whom you do not have fixed points. And so the connection to root finding is as follows. So if I'm given a function f, which I'm trying to find the root of, I can construct a new function from that function. Whose fixed points are the roots of f of x. Okay, so let me give you a simple example of this. Right, so if I have f of x whose root I'm trying to find, I can write a new function g of x of the form x plus phi of x f of x. Right, it's easy to convince yourself that when g is evaluated on alpha, which is a root of f of x, then I get alpha plus phi alpha times f alpha, and f alpha is 0, so I just get g of alpha is equal to alpha. So if alpha is a root of f, it is also a fixed point of g, right? So the goal is that studying fixed points help us better understand root finding. Okay, all right, so that's where we're trying to go with all this. So let me state first a theorem about fixed points and their existence and uniqueness. So this is about the existence and uniqueness of fixed points. Okay, so if you let G be C0, the interval from A to B, with G be a map from A to B to itself, right, then G has a fixed point alpha in the interval from A to B. And this is just a consequence of the sort of the intermediate value theorem, if you will, right, for G minus X, basically, right? And so if G of X, G minus X is 0 on either end, right, then you're done, basically. Yeah, and it's not possible for G minus X to be to have the same sign on both ends because of the way the intervals map themselves. Okay, so that's sort of the observation. Okay, anyhow, so furthermore, if G is differentiable on the interval from A to B, and there exists some lambda, which is between 0 and 1, such that the absolute value, the derivative of G at X is bounded from above by lambda less than 1 for all X in the interval from A to B, and the fixed point is unique as well. Okay. Okay. All right. So anyway, so that's something which is going to guide our study of fixed points. So one of the obvious questions to ask is, if you have something where the existence of the fixed point is guaranteed, how do you actually go about iteratively approximating it? And the way you do this is through what are called fixed point iterations. Okay, so fixed point iteration. Okay, so an iterative scheme to approximate the fixed points of G of X, right? Give a starting point alpha 0. Okay, and this generates a sequence alpha n, starting point n equals to 0 to infinity, by the rule that alpha n plus 1 is equal to G of alpha n, n greater than or equal to 0. So the basic idea is that you generate this sequence by repeatedly applying this map G, and as you might expect, if this sequence of iterates converges, it converges to a fixed point of G. Okay, so I should remark that this allows me then to connect it to Newton's method, because Newton's method can be viewed as a fixed point iteration of one of these maps whose fixed points are the roots of the original function g. Okay, so the remark is that Newton's method is the fixed point iteration for the function g of x, which is just x minus f of x over f prime of x. And it's easy to convince yourself that if alpha is a root of f of x, then g at alpha is alpha minus f alpha divided by f prime alpha. This vanishes, so that's just alpha. So if alpha is a root of f of x, it is a fixed point of this g of x, right? And the Newton iteration, or the Newton method, is just the fixed point iteration for this function g. Okay, so what we're going to do next is to establish various fixed point theorems as they pertain to fixed point iterations, and then we're going to use this to better understand the convergence properties of Newton's method. So let me stop here for now.